Okay, so last time we briefly discussed the rational numbers, and we showed that there's no rational number whose square is 2. So basically, we can summarize by saying there is no root 2. That would be the takeaway from the previous video. Today, I want to describe some of the algebraic properties of the rational numbers. And how we're going to do that is by describing the field properties of the rational numbers. So let's define what a field is. And so last time so lemma 1 was the proof that there's no square root of 2. So we're going to keep a running definition and theorem count. So this will be 2. Definition 2. A field is an ordered triple F plus dot, where F is a set and plus and dot we call these addition and multiplication. Are binary operations on F. So basically by that we mean each of these is a function that takes 2 elements of F and returns another element of F. So if you think about it like regular addition of numbers is a binary operation on a set of numbers. And these are binary operations on F such that the following properties hold. Okay, and I will list 10 properties. And that sounds like a lot, and it maybe is a lot, but a lot of these properties are, well, they should all be pretty intuitive, I think. And the first one is x plus y equals y plus x for all x and y belonging to F. So that is to say addition is commutative. Okay, the second one is that addition is associative. Okay, and by that we really mean like the value of this sum doesn't depend on bracketing. Okay? And the third one is that there exists a distinguished element 0 such that x plus 0 equals x for all x. Okay, the fourth one, and we call this 0 element, we call it an additive identity. The fourth one is that for all x in F, there is an element called minus x in F such that x plus minus x equals 0. And I won't harp on it too much, but clearly the additive identity is unique, and clearly the additive inverse of each element is unique. Moreover, by reading A4 with the roles of x and x inverse swapped mentally, we see that x is the additive inverse of negative x as well. Okay, so these four are axioms for addition, of course. And let me... Yeah. So these are axioms for addition. And, well, that's a little ugly. Let me fix that. And for multiplication, we have kind of one axiom that corresponds to each of these, but they're slightly different. So the first one, remember, is commutativity. Second is associativity. Okay. The third is identity, in particular, like the additive identity. And the fourth one is about inverses of elements. Okay, and we've described kind of how the addition behaves. But let's also describe how the multiplication behaves. Okay, so this is M1, and it states that for all x and y, x times y equals y times x. M2 is that for all x, y, and z belonging to f, the value of this product doesn't depend on bracketing. X, Y, Z equals X, Y, Z. Okay, but so if we denote the additive identity as 0, and we think of like the rational numbers as our exemplar field, what do you think we're going to denote our multiplicative identity as? Yeah, it's going to be 1. So there is a distinguished element 1 such that 1 times x is just x for all x. Okay. And the fourth one, so this is where things really get a little different, because we want to say every element has a multiplicative inverse, but we need to be careful here. Think about like the rational numbers. There's one element that doesn't have a multiplicative inverse, and it's the additive identity. So in particular, there is no number that you can multiply by 0 to get 1. So for all non-zero x, there exists an element, and we will denote this x to the minus 1, such that x times x inverse equals 1. Okay, so this should make sense, I think. We haven't done anything crazy yet. Like all of these, if you think about them in the context of the rational numbers, I think they make perfect sense. And for our purposes, you can take a class on field theory and like you learn all of these things in much more general settings. But for our purposes, right now, the most important example is the set of rationals. Okay, and I promised you 10 axioms, and so far we have 8. Well, That's because we still have two axioms to go, obviously, and these kind of are a little different. So the first one I will call MDA. And that means multiplication distributes over addition. And x times, in parentheses, y plus z equals xy plus xz for all x, y, and z belonging to f. Okay, so this kind of tells us, like, if we have an expression involving addition and multiplication, this kind of tells us a little bit about how they can interact. Okay, and this last one, I'm going to call it ND, and it stands for non-degeneracy. And don't laugh, it says that 1 doesn't equal 0. So the additive identity and the multiplicative identity have to be distinct. And, that might sound like a really silly thing, but basically the point of this is to prevent the degenerate field with one element from being a thing. So that's why we do that. And let me make a couple more remarks here. I'm just going to make some remarks. The first one is that for x dot y, we usually just write xy. This shouldn't be surprising. Like if you ever, I don't know, like went to like 5th grade or something. Once you took your first algebra class, you probably saw this. And I don't mean abstract algebra. I just mean like elementary algebra. And rather than writing, so it gets a little tedious to write this. So what we usually do we just say the field F. And yes, technically this is sloppy because, a field is an ordered triple with 3 elements. One of them is the set F, and the other 2 are these binary operations, but it's really tedious to write that. And as long as the context is clear, there's not really any there's not any possibility of confusion. Let's make a couple of observations. So there can't be like an empty field, right? And we know there can't be an empty field, right? Because there has to be an additive identity and there has to be a multiplicative identity by A3 and M3. And by ND, the smallest field has to have at least 2 distinct elements. Okay. I'm just going to give you this for free. It's not too hard to prove. The additive identity and the multiplicative identity are unique. By which I mean there can't be more than one additive identity or more than one multiplicative identity. It's not hard to prove it. Now, similarly, inverses are unique. given an element x, minus x is unique. And if x is non-zero, then x to the minus 1 is unique. And finally, we often write 1 over x for x inverse. Again, this shouldn't be like too surprising. I think that's all the remarks I wanted to make. Yeah, so we've defined a field. And I'm going to state this as a fact. Q is a field. With the usual addition and multiplication. I'm not going to prove that here, but it's true. Okay, it's true. And from the field axioms, we can actually prove pretty much every algebraic property about Q. I'm pretty sure we can prove everything we would ever want to care about as far as algebraic properties go. Not so much for the ordering properties, but we'll get to that in the next video. So, and just as an example of this, we're not going to prove everything as far as algebraic properties go. But let's just do this as an example. So if f is a field, and remember, we really think f plus dot, it's just we're being cheeky. If f is a field, then given x, y, and z in f, the following must hold. The first one is that if x plus y equals x plus z, then y equals z. The second one, if x plus y equals x, then y equals 0. If x plus y equals 0, then y equals minus x. And negative x is just x itself. I think I kind of mentioned that some of these were trivial earlier, but let's actually prove them. Because sometimes it's important to prove that you can put your money where your mouth is and actually prove these things that we call trivial. But in general, we won't be this pedantic in the future. Okay, proof. Let's just prove them one by one. So for A, if x plus y equals x plus z, then, well, what can we do? Well, we can add negative x on both sides. And we can do that by A4. Okay, and what we really want to do is just cancel out these x's, right? But we're kind of going under the hood a little bit and explaining why we can do that. And in particular, so we've added negative x to both sides. And what we want to do now, we want to rearrange these parentheses. And we can do that because of A2, associativity. Okay, and negative x plus x, Well, that's 0, but let's actually be a little more careful, because as we wrote it, x plus minus x is 0. We didn't say minus x plus x is 0, but we can use commutativity of addition, A1, to reverse the order. X plus minus x plus y equals x plus minus x plus z. Now, x plus minus x, though, that is indeed 0. And we used A4 to do that. 0 plus y equals 0 plus z. And I think we need to use, so we need the 0 on the right if we want to remove the 0. So we use commutativity once more. Y plus 0 equals z plus 0. And now we can use the fact that any number plus 0 is just that number. And that's A3. So we can drop these zeros at last. Okay. And you're like, why the hell did it take like 7 lines to do this? And the reason is, again, for demonstration purposes. In practice, we're never going to be this pedantic again after this proof. And since that was so slow, let's do B really quickly and note that it's just a special case of A in which z equals 0. So in particular, say x plus y equals x. Well, then x plus y equals x plus 0, because we can add 0 on the right side. And then by A, y equals 0. Okay, because we can cancel out that x on the left. Okay, very good, very good. Now, what do we want to do for C? I mean, we can kind of brute force this one if we want. Say x plus y equals 0. Well, then we want to do negative x on this both sides. And honestly, by associativity, we really don't even need to worry about bracketing these addition statements, so I won't. Okay, and then this is 0. Okay, and if you are a little uncomfortable with how quickly I've gone through these, especially this one, I encourage you to actually write this proof out yourself, and at every step, write out which axioms we are applying. And D, so remember, we want to show that negative x is just x. So x plus minus x is 0, right? And then by A1, negative x plus x equals 0. And this kind of suggests to us a symmetry in this definition of additive inverse. Because what we can do, we can actually read this definition with x and negative x mentally interchanged. And this shows that x plays the role of additive inverse for negative x. So by mentally swapping the positions of x and negative x in the definition, we see that negative x is just x. Okay, and that proves all four statements. Okay, so that proves proposition 3, or lemma 3, I believe we called it. And if you think about it, this kind of begs us to formulate corresponding properties for multiplication. And we can do that. I'll do it really quickly. We'll call it lemma 4. Let f be a field. And we do need to be a little more careful, though, because we've pretty liberally used negative x in this proof. So if we were thinking about like the corresponding statement for multiplication, we would want to use 1 over x, right? But remember, not every element necessarily has a multiplicative inverse. So we need to stipulate that x is non-zero. So if x is non-zero, then and xy equals xz, then y equals z. And we can think of this as like dividing through by x, or multiplying through by 1 over x, intuitively. And for b, if x is non-zero, and y is non-zero, oh, nope, sorry, and xy equals x, well, then y equals 1. C is that if x is non-zero and xy equals 1, then y equals 1 over x. D is just that if x is non-zero, then 1 over x is just x. Okay? And I'm not going to prove these. I just stated it for completeness. But if you want practice, I would encourage it as a good practice exercise. Okay. Now, let's do one more proposition. Okay, that was lemma 4. So this is just a few more properties for fields, and then we're kind of done proving these basic properties. I mean, we could do this all day. We could do it for a very long time. However, that's not really the purpose of these videos beyond this one. Let's let f be a field. Then, for all x and y in f, it holds 0 times x equals 0. Doesn't it feel silly to like state these things that we've used freely? If x is non-zero and y is non-zero, then xy can't be 0 either. Negative x times y equals negative x times y in parentheses equals x times negative y. And finally, negative x times negative y is just xy. Okay, so for the first one, 0x equals 0. So let's consider 0x plus 0x. And think about, what is this equal to? Well, we can factor out the x on the right. And we are left with 0 plus 0 in parentheses times x. But 0 plus 0 should just be 0, right? So this is just 0x. Okay, and now we can subtract off a 0x from here and from here. And we're left with 0x equals 0. Okay, so that's not bad. Okay, so suppose x and y are both non-zero. Well, what we can do we have that 1 is equal to x times 1 over x times y times 1 over y. Right, because this is just 1, and this is just 1. Okay. But hold up, we can rearrange this. And we get xy times 1 over x times 1 over y. But hold up, this is just 0 because we assumed, for the sake of contradiction, oh, I'm so sorry. I meant to assume for the sake of contradiction that xy is 0. We have that this is 0 over xy. But that should just be 0. So 1 equals 0. Violating ND. So basically, if it was possible for xy to be 0, even though x and y were non-zero, we could show that 1 equals 0, which is ridiculous. So this is an impossibility. Okay. For the third one, let's just compute. Negative x times y plus xy equals, and what does it beg us to do? It begs us to factor out a y on the right. Minus x plus x times y. Well, this is 0 equals 0y, which is just 0. So this shows that this and this are additive inverses for one another. So, in particular, this must hold. Okay, and we can do a similar thing because we've proven like the first of these two equalities, but we need to prove the second as well. So similarly, x times minus y plus xy, and we can factor out an x, minus y plus y, 0, equals x times 0, which is just 0, of course. And this shows also that these two must be additive inverses. And then putting it all together, we get, well, minus x times y equals negative, in parentheses, xy, equals x times negative y. Okay? Which is exactly what we were assigned to prove. Okay, the fourth one isn't that bad. Negative x times negative y equals, well, we can pull out that first negative. And we can pull out the second negative. We're using c in both of these, if you think about it. But the negative of a negative is just the original element. And we're done. Okay, so we kind of went through the latter part of these kind of quickly. But I think it's good to kind of wrap up here with a couple of notes. And the key takeaway, because Q is a field, all of these properties hold in Q. Okay, and, I guess where we're going, we're not so much interested in Q as the set of real numbers, but it turns out the set of real numbers will also form a field. So, and because we proved these in the general setting of arbitrary fields, once we've shown that the real numbers form a field, we can actually use all of these freely in that setting for no extra work. So that's really the power of this general concept. And indeed, if we have any other field, these things also apply there, even if it seems like a really unfamiliar setting. And I guess, if you want practice for fields, there's a couple of things you could do. Okay. And that is, so the first one is to actually prove lemma 4. Where we stated analogs of all the properties in lemma 3 for multiplication. And then, if you still want more practice after that, write out the proof for lemma 5 noting at each step what property we used. Okay, and sometimes those might be axioms, and sometimes it might even be earlier things that we proved. Okay, so I think that's a good practice for people who never did field stuff before. And next time, so this time we kind of thought about like the algebraic properties of the rational numbers. Next time we'll think about the order properties. And we'll make those explicit. And then we will actually talk about how the algebraic and the ordering properties interact, and Q forms what is called an ordered field. Okay, so that's all for today.